Thank you, Philip, and thank you too to the organisers for the opportunity to come and share with you a little bit of knowledge. And I empathise with Fabio. I think you'll notice he's going a bit bald. Well, organising conferences, that probably accentuates that, and I've been involved in one that's in 3 weeks in Australia, and I know it's very time consuming, so thank you to him. I just want to acknowledge my co-author in what I'm going to talk about, because a large portion of what I'm going to talk about is related to genetics, and Sue Hatcher is my co-author. She's a quantitative geneticist, and over the years I've had the privilege of doing a lot of research with geneticists, and that's an interesting experience if you've never done it. So just to tell you, if you're in Drew Ferguson's talk this morning, of course he had a nice map of Australia. This is just to tell you exactly where I come from, which is, whoops, go back. This is where I live here, this little place in central west New South Wales, and my co-author Sue is at Trangie Research Station, which is about 2 hours away, quite a large station, 12,000 acres, in the past run up to 7,000 sheep in experiments, and at the moment it's been overrun with Angus cattle looking at metagenesis. You'll notice also that there's a country down to the southeast of us too, that we often associate with. Except at rugby time. I just want to give you a bit of an overview of the things I'm going to cover. I'm going to talk about genetic, and it's in the terms of genotype, where we've got a mix of different genes. We won't cover major gene effects, things like myostatin, caliphage, SOA. They're not in the paper. And I want to emphasise also, when we talk about this subject and when we review the area, and it probably applies to every area, about looking at robust designs in the experiments that we undertake, but also when we do the review, to look at why someone might get a particular result which in itself might stand out and be unusual. We'll look a little bit, and that was the part of the charter of my task, was to look at gender and age. I did actually cut back the charter of my task because there was no way I could have done the original one. And then we'll have a look at some lessons from genetic improvement, particularly in the context of lean meat yield production and the application of new traits in industries. And then I want to actually frame it in the context of Australia and how some of this knowledge over the time has actually been integrated into production systems. So what it's doing is it's taking science and applying it in industry and making an application. And that's a very important trait of what we should do. So just a little bit of background. Can you hear me okay? I'm just not sure about this mic. Is it okay at the back? Just yell out if you're falling asleep. So meat quality traits have become obviously more important to consumers. And genetic change is occurring through a number of different approaches, and we'll talk about some of those in a minute. And the question is, what's the context or what's the impact of genotype in that whole scenario of meat quality and consumers? And as I've said, some of the caveats that we need to apply to what's published, and as we look at information and distill it, particularly traits like tenderness and colour and so on, we need to reduce the processing effects. If you want to really look at what is the genotype effect, what are the genetic effects that are going on, get rid of the processing effects, because often they confound experiments. And I can demonstrate that by looking in the literature where that's the case, and you come to the wrong conclusions. So there's also many studies that have been conducted in this area where essentially the genetic representation is insignificant. Like it's not enough, and you're not really sure, is that a real breed effect per se, or is it actually simply a sire effect? And it also helps to know where the sires are that you're evaluating sit within the genetic spectrum of that particular breed. And we also need to avoid confounding. Often slaughter days, things like that are confounded, and that can mess up your understanding. So this is some results from some work that we did a number of years ago with a whole range of different genotypes, sheep genotypes, different size, as you can see, Tex or Pole Dorset, different ewe crosses, and then looking at some of the meat quality traits that are associated with whether a product fits in and is good enough. And you can see basically if you look down those lines, whether it's measurement of longissimus muscle or semimembranosus, there is basically no difference there in those particular genotypes in terms of tenderness. And the caveat on this, of course, is that that product's aged for 7 days. So what we're trying to do again is to take away the processing effects and look at actually what the true genotype effects might be. And even when you eat the product, right over there in what will be the right-hand column, the tenderness traits, again, with in this case, a trained panel, no difference. In this case, the experiment had a minimum of 7 sires per breed, so we're confident that we're starting to get some representation of those particular genotypes. So, as I've said, probably some sort of breed ranking, not single sire effects. We apply the ageing, and there's some work that's been done in Ireland demonstrate the same sort of thing, that if you conduct these experiments in a rigorous way, often these genotype effects actually are not evident. So I just want to talk now a little bit about a major program of research that's been going on in Australia now for actually quite a few years, called the Sheep CRC. It's a cooperative research centre, and it actually involves all those groups that are identified there in red, right across the eastern seaboard of Australia and over to Western Australia. And as a part of the more recent Sheep CRC, we ran an information nucleus. So this is actually a large genetic experiment, and you'll see some of the outputs of that as I go on. But essentially running 5,000 sheep across those sites, all genetically linked by the same sires, so you can actually take account of environmental effects. And out of that program, we've actually slaughtered 10,000 lambs over 5 years and measured about 30 different meat quality traits, and on other animals in that program up to 300 different traits. So as I've said, 5,000 years, we've slaughtered these 10,000 lambs, and we measured a lot of those traits at the bottom there, and I'll focus on some of those. So things like iron, zinc, omega-3, the health claimable fatty acids, shear force, pH, meat colour, and indeed some eating quality using sensory systems developed in Australia under the Meat Standards Australia brand. If you look at this particular slide, it comes from some recent work that Lisa Lottie-Pania has published in a special edition that we had earlier this year. And this has got some sire estimates, if you like, in terms of 3 different sire types. So we're talking about terminal sires, maternals and merinos. So straight merinos, maternal breed, and the terminals. And you can see in the yellow that the data seems to suggest that the terminals actually might produce something that eats not quite as well as some of the other sire types there. There's a reasonable number of animals in that experiment, 1,500. Each of those samples in there is eaten off by 10 people, so quite a lot of testing. So, as I said, the data suggests that there might be a sire type effect, but again, you have to look into the actual construct and design of the particular experiment that you're focusing on. In this case, because we have breeding values on all the sires that we used in this program, we can actually look and see how those sires are ranked against all their contemporaries. In this case, if you do that, these terminal sires had breeding values that were actually leaner than the average. So I would contend that that actually drives the effect that you're seeing. So again, you need to look at the outcome. There's no doubt that fat influences eating quality, no dispute about that. Some Scottish work actually by a Uruguayan who was working in Scotland. I'm not sure, I haven't seen her around, but I know she's published some papers in this conference. And she reported a real reduction in intramuscular fat, in a breed effect, in terms of tenderness. And the question is, was it due to an IMF effect? Was it a real breed effect? What was actually driving that? This is actually the beef. I'm cheating a bit here, but this is the beef scoring system used in Australia as a part of the Meat Standards Australia, just to demonstrate the range that's possible in terms of IMF. So there is evidence of a genotype effect on IMF, and in fact, if you look in the literature, you will see other breeds. This is some Czech work here that showed that you could actually have some very low levels in particular types of animals, and those first animals actually came into Czechoslovakia from Holland, I understand. So there are differences in terms of IMF, and there are genotype differences between types. And if you look at the implications of that for eating quality, it's likely that those sort of effects would actually impact on eating quality. And again, from Lisa Lottie's work, you can see there down the bottom, it talks about a range in IMF from 2 to 7%, and the overall liking decreased by 10 points. So this is on a 0 to 100 scale, effectively, which the panellists only probably used from 20 to 80. So it's quite a significant effect. And again, you get the same effect in the top side. One of the other major outcomes of looking at studies in terms of genotype, and we've seen this particularly in Australia, more so than some of the other literature, because we run within our production system some straight merino animals. And you can see in the yellow at the bottom particularly, this is again the study I referred to earlier. We're talking about data here from nearly 2,500 lambs slaughtered over 3 years, with quite a good representation of sires. And if you look at the yellow down the bottom, you'll see that there is a tendency for the merino breed particularly, and the border to a lesser degree, to have an elevated pH at 24 hours sort of post-mortem. But the interesting thing, and you can see that goes right across the different muscles. You can see it's in the ST, which of course we know is a more anaerobic muscle, probably a better indicator of stress because of its different glycogen capability. If you go over to the far corner and you look at the research animals, and this was a very small experiment that was a part of a PhD in Australia a number of years ago, where they took some of these crosses and actually slaughtered them in a university-type abattoir, so with minimal commercial application. But the interesting thing was that the pH effect totally disappeared in that case. And so one could assume from that a lot of what happens in the merino breed is actually driven by the things that happen before that process of slaughter. I'd like to say that, unfortunately, when we've done the live animal studies to look at some of the behavioural traits in merinos, that they don't actually, it doesn't actually correlate with an increased pH, and they don't seem to be more agitated when you go to slaughter. There's a recent paper just been published in Australia on this in terms of some other behavioural indicators, but again, the message is not that clear. And it's an interesting phenomenon that really, in the literature, and particularly in our context, hasn't really been solved. We really don't know why this happens totally, but it's not as simple as just these animals not coping with the slaughter process. In terms of colour effects, really there isn't a lot of very strong evidence that you get genotype effects when you measure colour objectively. And again, you have to bear in mind there may be pH-driven effects, and so you have to actually take those account. You can't just look at one trait in isolation without knowing what happens with other traits that might impact on it. But there is some evidence, particularly where we take meat and put it under simulated retail display, that brownness development, metmyoglobin formation, actually can be accelerated in certain conditions. And this again is some data that comes from some recent, I suppose more recent work back in our first sheep CRC that Robin Warner's published, and Robin's speaking next door and competing against me. But you'll see in the yellow there, what's the data in that table is basically looking at the ratio that you would measure with a Hunter spectrophotometer. So it's looking at that ratio of 630 to 580, which you can have some debate about what it actually indicates. But if you look there in the yellow, you'll see that where we've taken a muscle, in this case this is quadriceps femoris, so this comes out of the hind quarter of an animal. You might know it as the round or the knuckle, depending on which country you come from. You can see that the values in these older animals, after that period retail display, that ratio is actually lower. So that's indicating that there's actually a faster rate of browning. The next one in the yellow has an odd value in it, which tends to inflate it. And just to reinforce this, in this most recent sheep CRC, recently published as a part of that special edition, some more data on the change in colour stability and affected by, in this case, sire type, in this case, merino sires. And when that data was actually very eloquently modelled, it demonstrated that basically if you had merino genes in there, you had a high pH and a high linoleic acid concentration, then you were going to actually drive down colour stability, so it was going to be less stable. So there's no doubt that there's some impacts there also of the genotype. Now, in our program we selected these particular minerals, iron, zinc, as being important for, obviously, for human health, and other people have talked about those earlier in the week here. Also, the full fatty acid profile on all of those 10,000 lambs, but with a particular focus on the omega-3 health claimable, the DHA and the EPA. And again, some of the data that Lisa Lottie has published from quite a large number of lambs, 5,500 lambs, shows that basically there's some pretty small differences between iron and zinc right across the major sire type effects. And this is across 8 different environments. There was some data presented the other day from Uruguay which indicated differences between locations, and essentially across those 8 production sites in Australia we get very little variation in the level of iron and zinc across those sites. So it's not something that nutritionally we would see as being majorly affected. And, you know, there were some significant differences in Lisa Lottie's work. You have to be a little bit cautious about how you interpret this data. There is a rule that, of course, the greater numbers that you get, the smaller your standard error, and then the more likely that you'll actually find a difference. And so you have to actually be a bit pragmatic. And if you look at her data, there will be some differences, but in practical terms, they're small. Whoa. Back. If you look in terms of the fatty acids, particularly I said the EPA and the DHA, and I don't have time to talk about all the other ones that we've measured, there are again some small differences due to genotype. And, you know, again, if you look at the second point there, merino dams, if you had a merino dam, you're likely to get, you know, approximately 2 milligrams per 100 gram of muscle more than from crossbred lambs. That's from a data set of about 2,000. But overwhelmingly, we know, and from other work that we've done since, of course, nutrition has a much larger effect in terms of altering that particular trait. So if you want to alter it, nutrition is your simplest and easiest way to do it. So I just want to talk now a little bit about genetic parameters, because if you want to have a genetic selection program, you obviously need to know the genetic parameters. You need to know how heritable the trait is. You also need to know how it is genetically correlated with other traits. Right across the whole of the spectrum of traits, production traits. And really until recently, and until this program in Australia in terms of sheep, we really didn't know what the heritability of a lot of these meat quality traits was. And that was a part of the geneticists developing this weird and wonderful, huge experiment for other people to become involved in. But the data that's now published shows that some of those traits are actually high to moderate heritability. So what that means is that there is scope to genetically select by developing the appropriate breeding objectives. You can select for particular traits in terms of sheep, in terms of meat quality. And you can see here the heritability. This is for 5-day aged shear force loins. The heritability is 0.27. The standard error is very low. Again, a reflection of the numbers, but it gives you some confidence in the trait itself. In the middle is some eating quality data that comes out of that Scottish group again, that shows you that those eating quality traits are not really that strongly heritable in terms of selection. And the interesting one that came out of our work was the very strong heritability for IMF at the bottom, 0.48. You know, geneticists get really excited when they see that, because that means you can make significant change genetically in that trait. Some of the other traits that we've measured, and I've tried to highlight in the yellow, the ones that are a little bit stronger in terms of heritability. It tells us there that, in fact, retail colour stability is a trait that could be selected for. So you could actually select and make selection decisions in sires that would have implications in the progeny themselves. and the same for zinc, and to some degree also for DHA. But as I said, if you want to change fatty acid type profiles, go and find a nutritional way to do it, and you can do it straight away. You don't have to wait for a selection program. As I've really covered the first point, I suppose. The important thing is that in Australia, a decision was made as a part of generating this information, and with a focus on the end user, who ultimately is our consumer. And in our case, as Drew said this morning, we export more than 50% of the lamb that we produce in Australia. Two traits were selected for development to go into our national selection program, and they are IMF and shear force. But the only way that we could do that, obviously, is by genomic breeding values. You can't use quantitative genetics to select for these traits because you can't measure them in the sires unless you kill the sires, and that doesn't really happen. So in this case, this is where genomic breeding values have a real place in the industry. They have some limitations, and I think actually Temple was hinting at a few of those limitations this morning, but these are the two traits that we now have in Australia research breeding values for IMF and shear force. So breeders of animals can actually get research breeding values back, which tells them where those animals will rank for these two traits, and then they can make decisions about how they will use those in their breeding programs. Now, my task was also to cover gender effects. It won't be as extensive. Despite what Drew might have said this morning in looking at the New Zealand data that, entire animals in New Zealand don't tend to produce tougher meat, I think you've got to put that in the context of the production system in the country. New Zealand historically slaughters very young and lightweight animals. In Australia, our average carcass weight is in the order of 21 kilos. They're much heavier than New Zealand. And if you look at the evidence, there's no doubt that if you have entire animals and you keep them longer and so forth, the impact of being entire actually increases. If you go to the castrates and the ewe lambs, there's obviously no difference from the literature. And if you do process entire males, you certainly need more care through the processing system to avoid meat quality issues. It's not an issue for us in Australia. You would almost find no lambs produced as entires. And it's interesting how industries evolve over time. When we started in Australia with a focus on the export market in the early 90s, we introduced the short scrotum, the crypt orchid, into the production system to try and elevate the carcass weight. But the processing industry reacted very violently to that, and there wasn't much adoption. And what happened through that simultaneously was that genetic improvement actually allowed us to get to the same levels of carcass weight at fat levels by genetic improvement, as opposed to actually having them entire. And so there's virtually no use of them in Australia. In terms of age effects, if you look through the literature, there is no doubt that there's some significant changes as lambs mature and then process into that older age, particularly around the 14, 15-month-old age. And I'll show you some data in a minute about that. There was some work we did in the first sheep CRC where we produced about 600 lambs. These are all genetically identified. And then we slaughtered these animals at 4 times as they grew, right through to 22 months of age. So a nice sequential study. And you can see here the numbers that we slaughtered at each of those ages, and some of the meat quality traits, particularly in terms of the colour traits, and very clear evidence that as you get older, and this biochemically fits in, particularly the level of myoglobin increases as animals age, and you can see there that the A values increase, the L values, how light or dark it is on that spectrum, decrease, so it becomes darker. And it seems around that sort of 14-month-old age, around then is some sort of critical time. The interesting thing too in shear force, if you look at the top side, a muscle historically has increased collagen, becomes increasingly insoluble. You can see that there's a dramatic effect in terms of age. And all of that product there is all those shear force samples are all aged for 7 days. So we're trying to eliminate the processing effect. There's no doubt that that's a clear age effect. And that follows through into later work that we've done in Australia, in our Meat Standards Australia program for grading, and it's quite clear. Topside is a very tough muscle in relation to the others. These are some of the animals that we had in that experiment at 22 months of age. These animals, we had carcasses here of up to 60 kilos. So these are big animals going through the whole full spectrum, plateauing in terms of their maturity. And a mix of different types in there. You can see merino at the front and one of the crossbred types. I've kind of covered, I guess, most of those. It certainly is that colour effect is, it is a myoglobin-driven effect, and it certainly is independent of pH. And the toughness in the topside is just consistent with the work that Owen Young did in New Zealand a number of years ago. Obviously, there is an interaction with muscle. And there's nothing new about that, but that has to be taken into consideration, particularly when you're developing eating quality programs. And the interesting thing, of course, is that counter to that is that IMF tends to increase as animals get older. So you get one trait that is favourable and you get another one that's negative, and you've got to try and balance them. But on the balance, if you want to really summarise it down, the younger you can kill these animals, in this case sheep, and it doesn't matter, it's the same in beef, the better it's going to be. Now, just in terms of a case study, I just want to put it into the context. All this knowledge is accumulated, but what do you do with knowledge? It's no point in accumulating knowledge unless you actually apply it. And this is the same of whether you're working with processes at the post-farm gate or whether it's a production system. This is a bit of a snapshot of the Australian industry. In the 1980s, lamb certainly domestically had a very poor image. It was considered a byproduct of the wool industry, and our industry was valued at about 1.1 billion at the time. There was an emphasis put on an R&D program to lift the weight of slaughtered lambs and reduce fatness. So we're talking about lambs that weigh 24, 23 kilos carcass weight, and in our system would be a fat score 2. So these are quite large, with the idea of trying to expand our overseas market into places like North America and countries like that. And one of the key traits one of the key factors that contributed to the success of that program was indeed this focus on genetic improvement. And we in Australia have this program called Lamb Plan. It is a national performance recording system, so all the breeders of terminal size in Australia can be involved in that program, and it will actually then give them an index on their rams for a range of different breeding objectives. And all these things have got to be put in the context of breeding objectives. And I think that's partly what Temple was actually emphasising this morning, is that you need to actually think about the whole animal, and the whole animal targeted to particular markets, and what do you need in that animal, and not focus just on one trait. And I'll give an example of where I think we did that in the past, and we had some warning things coming up. We have a unique production system in Australia that could allow us to actually integrate that information into that production system, so this genetic improvement system. And I'll give you now a demonstration or a diagram of that. So across the top we have, if you start on the left-hand side, we have merino ewes, merinos over merinos. They obviously produce male lambs, which historically might have been kept before for wool. Now they are basically all slaughtered because of the change in the wool market. We have merino ewes that would be joined to a terminal sire, and they would produce first cross ewes, which then themselves could be joined to a terminal sire to produce a second cross lamb. So what we're getting here is the advantage, the benefit of hybrid vigour. So we're able to introduce different gene pools and increase growth rate and those sort of things through that process. But on top of that, we're also able to target, for instance, the maternals and put selection on the maternal for reproduction, so that we can improve reproduction from a genetic point of view. The beauty of this system is that you can target, as I said, different sire groups, in this case, say the terminals, and have a genetic improvement program, in this case focused on growth, muscling and fat, and therefore have a profound effect on your industry, and that's actually what's happened in Australia. We have the first cross weather lambs also coming out of that system. So we have lambs coming out of different genotypes from that system. Just to give you some perspective, I guess, and just keep it in mind in terms of the crossbred approach, if you look at this data, which comes, I think this is data out of the UK, you can see that as you introduce the crossbred influence into this, as you bring in some genes from another gene pool, that you improve the carcass weight in this case. But the thing to note is that in the last line, where you've got a Texel by a grey face ewe, you don't get any advantage. And that's because you're still putting in Texel genes. And in this case, you've got then 3/4 Texel genes. If you want to maximise the effects of hybrid vigour, then you put in a sire, which is also a crossbred, the 4x4 cross. And a fellow in Australia a long time ago, T.S. Chang, who worked for CSIRO, demonstrated this very well, that the maximum hybrid vigour that you would get is by bringing in some sort of terminal crossbred sire also. So the benefits of crossbreeding, of course, it's obvious. If you have a second cross lamb compared to, say, a first cross lamb, you'll increase the growth rate significantly. And it gives you greater flexibility to do what we've tried to do in Australia, and that is to target particularly markets where we want large and leaner lambs. And as I've said, we can also improve our base flock, because we have genetic improvement programs for the base ewes also, and also now for merinos for a whole host of different traits. Just want to show you, we talk about, animals fitting into particular environments. This is the sort of environment that you might characteristically find a merino in. I just want to inform you that that's the South Island of New Zealand. And normally when you go to New Zealand, they show you the nice green pastures. So I don't know whether there's any Kiwis here, but that's animals fitting into their environment. And you'll find merinos in those sorts of environments in Australia also. These are some lambs that we produced out of the sheep CRC program, just to show you what you can achieve. These lambs were slaughtered at 5 months of age and had carcass weights of 30 kilos on average, with fat scores between 2 and 3. So genetic improvement can have a major impact. And this slide here demonstrates some of that improvement that we've seen in Australia. So on the red line down the bottom, you've got the increase in the index value of terminal sires across the country, and this allows all of the different studs to basically be indexed, and it doesn't matter what the index is. You can choose indexes, so you can put emphasis on particular traits. And the caveat, of course, in all of this is that if you want to use genetic improvement like this, you also need to use visual appraisal to make sure, again, something that Temple mentioned this morning, that make sure that the animals are actually fit for the job, is got to go with the process. Don't let geneticists alone produce figures in rooms. It's dangerous. Okay? So genetic improvement. In Australia, we have 3 breeding values, as I've sort of mentioned, one for muscling, another for fat and growth. And when we put that together, and I haven't covered all the other things that went into that R&D program, which are processing and so forth, but we've seen our carcass weight in Australia increase from 17.5 kilos in the 90s to approximately, as I said, 21 kilos now. And it was interesting that back in sort of the mid-90s, when there was a real emphasis on selection for increasing, say, lean meat deposition, that... Too close? Oh, okay. I just want to make sure they can hear. There wasn't really a focus on meat quality as a part of that process. It was a production-driven system. And when you do that, just as I've mentioned, you can run into issues. And in the next slide, we want to demonstrate that if you look in this table here, what you've got are 3 eating quality traits that were derived from using our MSA system in Australia. So this is using real consumers. Each consumer tests 6 samples, and each sample itself is tested 10 times. And in the middle of that table, you can see what are the regression coefficients for those breeding values for muscle depth. So this is the muscle depth of the sire. This is the breeding value of the sire. And immediately, those of you who are still awake will work out that all those coefficients are negative. So what it indicates is that as you increase the muscle depth of the sire, in this case, you drive down the tenderness of the progeny themselves. And it wasn't greeted with a lot of enthusiasm at the time by the geneticists, I can tell you that, and particularly when we published this work. But what it's done since then is to really spur on the fact that we need to focus on meat quality traits. So we need to have that holistic approach to the breeding program to make sure that we don't actually drive down what are important traits. And it didn't matter. Those 3 traits are really highly correlated: tenderness, juiciness, and overall liking. And what it's done is, as I've said, it's led to a focus to look at generating heritability traits that we can use as genomic breeding values. So, as I said, we have genomic breeding values now for shear force and IMF. It does require that your blood test and DNA analyse so that you can then derive that using a SNP chip. That cost at the moment is around about $17, I think, per animal. It has, the geneticists have suggested that we can actually increase, hard to measure traits, these traits that you can't measure through quantitative genetics and improve through quantitative genetics, by up to 20%. So it has real potential to help us improve the sort of animals that we would produce. So just talk about some application, I guess. Think about what are the main messages that come out of all of this. Well, certainly hybrid vigour. It's something that you can capture. It's something that you can apply. And, I'm always intrigued when I talk to breeders about, particularly in terms of breeds, everyone's got the best breed. But what you've got to appreciate is that within each of those breeds, there are good animals and bad animals, and what you need is to identify those animals. And that's what genetic improvement allows you to do. If you focus through terminal size, it can be very effective. You can get change. As I've said, in Australia, what we tried to do, because of those colour changes and so forth, we tried to protect the lamb brand. We think it's actually it's a marketing tool to be able to say that our product is of good colour and related to the other traits. So, just in terms of some conclusions, there's no doubt that merinos do produce a higher pH. I say the cause is still unresolved. Genetic breeding values are going to help us to improve some of these traits. And very important caveat that we need to develop appropriate breeding objectives and selection criteria. So you need to have a balanced breeding objective for where you want to go that balances those traits and also thinks about fitness for purpose. That's also very important. If you want good meat, I would argue eat young animals. And if you look at the Australian industry since we've implemented these changes, you can see now that it's actually worth a lot more in dollar terms. Our exports are now over 50%, up from 22% in 1994, and we export to a lot of countries. And what I'm trying to convince you today is that application of knowledge to industry can bring industry change, but you've got to work with industry.